Hello everyone, my name is Jacob Fixel and I'll be presenting on generalized Bayes quantification learning under dataset shift. I want to first define quantification learning. The goal of quantification learning is to estimate the distribution of a discrete outcome in a population of interest, which we will call U. For example, the percent of individuals in a country who die of a certain cause of death. In this toy example, we have three classes of orange, brown, and blue, and I've represented the true class by the filled-in color. The parameter of interest which we want to estimate is p, and the true value is 20%, 30%, and 50%. However, in quantification learning, we don't have access to the true classes, but rather we have access to a potentially large number of covariates that are thought to be predictive of the true classes. For example, we may have access to symptoms individuals were experiencing before they died. We can then use the covariates to obtain predicted classes for each individual. These predictions come from a prediction algorithm that has been trained using a separate training set, which I will talk more about shortly. These predictions can be single class predictions in which each individual is predicted to belong to a single class, or they can be probabilistic or compositional, which is common for Bayesian algorithms. A naive approach would be to simply use the empirical average of the predicted classes to estimate the population distribution. In this toy example, I've represented the algorithm single class predictions using the outline color, and we see that our naive estimate of the distribution p is 30%, 30%, and 40%. However, the naive estimate is typically not a good estimator because algorithms are not perfect and will misclassify instances. Returning to our toy example, we see that there are a number of individuals for whom the outline or predicted class is not equal to the filled-in or true class. We can decompose the naive estimate for the percentage of individuals who belong to class J as a sum over the product between the parameter we want to estimate, which is the true percent of individuals who belong to class I, and the probability of being misclassified from class I to class J. If we could estimate these misclassification rates, which we arrange into a misclassification matrix M, we could recover the true distribution using the misclassification rates and the naive estimate. One strategy might be to use the data that we originally used to train the prediction algorithm to also estimate the misclassification rates via cross-validation. However, this will often result in a poor estimate of the misclassification rates due to dataset shift, in which the distributions of the outcome of interest and also the conditional distribution of the covariates given the true class are different between the population that was used for the training data and the population of interest or test population U. For example, we may train an algorithm to predict the cause of death from symptoms using deaths from India, but then apply this algorithm to subjects in Mexico. Because the symptom data is often collected using verbal interviews with relatives who lived with the deceased individual, the distribution of symptoms conditional on the true cause of death is usually not similar between countries with different cultures and health systems. Our proposed strategy to mitigate dataset shift is to use a small dataset relative to the number of individuals with just covariate from the population of interest U, for whom we have covariates and thus algorithm predictions in addition to the true class. These individuals come from a convenience sample, which is a subpopulation of U, and we will call this convenience sample L. This convenience sample may not be representative of the full population U. For example, we may be only to get true causes of death for individuals who died in a hospital, but not in the community. We can then use these individuals to estimate the misclassification rates from the pre-trained algorithm in our population of interest, under the key transportability assumption that the misclassification rates are the same in the subpopulation L and the population of interest U. In previous work, we proposed the method for joint estimation of the misclassification matrix M and the true population distribution P if all the distributions were single class. We use a multinomial likelihood for the algorithm predictions, conditional on the true class for the labeled set L, as well as a multinomial likelihood for the algorithm predictions in U, which incorporates the decomposition of the naive estimate for P, which I discussed earlier, using both the misclassification matrix M and the parameter of interest P into the likelihood. As I mentioned, the dataset for which we have the true classes may be very small, which could cause high variance when estimating M. We thus use a Dirichlet shrinkage prior on M, which a priori gives high weight to M being the identity matrix, which corresponds to no misclassification. When we have a small number of individuals with labeled classes, our Bayesian estimate of the true distribution P will thus correspond to the naive estimate, while as the number of individuals with labeled classes grow, our estimate will correspond to the maximum likelihood estimate. The limitation to this previous approach is that it is only appropriate for when we have single class predictions. However, many algorithms give compositional predictions. One way to handle this in the Bayesian framework is to use a Dirichlet likelihood, but the issue with this is that it does not allow for zeros in the data, which would make it unable to handle single class predictions. And it is importantly subject to model misspecification, which is extremely likely in the setting where we're trying to model algorithm predictions with no expectation about the true data distribution. Rather than assuming a specific form of the likelihood for the compositional data, we propose to generalize our definition of misclassification and use only a first moment assumption on the expected value of the algorithm prediction conditional on the true class. When we only have single class predictions, this expectation of course can be interpreted as probabilistic, and we recover our original model. As an intuition into how we mathematically incorporate a first moment assumption instead of a likelihood into our Bayesian model, we essentially create pseudo-data for each subject in our dataset, with a large number of pseudo-individuals for each real subject. And in this toy example, I'm only showing 10 pseudo-individuals. The distribution of the algorithm prediction amongst these pseudo-individuals thus corresponds to the compositional for the prediction for that individual. We can see here in this example, the algorithm predicted 20% orange, 40% green, and 40% blue. And thus the outline colors for the pseudo-individual correspond to those proportions. Because we know the true class for this individual, because it is in our labeled set L, they all have the same filled-in true class orange. Because we then have discrete pseudo-individuals, we then use a discrete likelihood or multinomial likelihood for these individuals, and then downweight them in the likelihood to account for the fact that we've artificially increased our sample size. Mathematically, we use a loss function rather than a likelihood for Bayesian updating. Our loss function is the Kullback-Leibler distance, or KLD distance, between the compositional algorithm predictions and the expected value of the predictions. If we were to minimize this loss function, it would be equivalent to minimizing a quasi-multinomial likelihood, and it is identical to minimizing the multinomial likelihood if the predictions are all single class. We also use the same loss function to estimate the parameter of interest P using the expected value of algorithm predictions for subjects from this population of interest U for whom we do not have the true classes available. To obtain the posterior distributions for M and P, we rely on the theory of generalized Bayesian posteriors developed by Basiri, Holmes, and Walker, which shows how we can connect the data to our parameter of interest by replacing the likelihood in a traditional Bayesian posterior with an exponentiated negative loss function. By substituting our specific KLD loss function into this formulation, it allows for generalized Bayesian updating using our shrinkage prior on M. We call this method Generalized Bayes Quantification Learning, or GBQL, and our generalized posteriors can be obtained using a Gibbs sampler using the pseudo data detailed in our paper. Our approach can also incorporate uncertainty in the class labels, which may happen if, for example, the labeled classes are obtained using crowdsourcing. Rather than a true class label Y, we instead have a compositional belief vector B for each individual in our labeled dataset. Through iterated expectation, we could easily incorporate this belief vector into our loss function by replacing the true single class Y with this belief vector B. Finally, we allow for ensemble quantification by incorporating predictions from multiple algorithm. With this ensemble algorithm, we allow for algorithm-specific misclassification matrix, but because each algorithm's loss function shares the common parameter of interest P, this ensemble algorithm gives a single estimate of P, and thus we do not have to choose between estimates between different algorithms. And we can formally do this again through our KLD loss function. To demonstrate the advantage of our method, we use this Population Health Metrics Research Consortium, or PHMRC, dataset, which has symptoms and true causes of deaths for thousands of individuals in 4 different countries. We choose one country as the test data, which we split into an unlabeled and labeled set, and train several algorithms using the other 3 countries. We then repeat this for each country as the test set. For each country, we know the true distribution of a small number of causes of death, and we compare this true distribution versus the estimated proportion. In this plot, which shows the results from our GBQL quantification, each row represents a different algorithm, and each column represents a different country which is being used as the test set. The y-axis is an accuracy metric for quantification, in which a higher score corresponds to higher accuracy, and the x-axis shows the number of individuals that we use in our labeled set to estimate the misclassification matrix M. The green line is the GBQL method, while the blue line is the naive estimate, and finally the red line is the estimate when we use M using the training data rather than the test data. We can see that as the number of individuals with labels increases, our method uniformly outperforms the other 2 methods. In addition, you can see the effect of shrinkage, with our method performing the same as the naive method when we have a low number of labeled observations. Finally, we wanted to show how the ensemble quantification performs relative to using the single algorithms. We show that for each country, when we have a low number of labeled observations, the ensemble estimate in red performs approximately in the middle of the individual algorithms, which we show in the different colors. Importantly, the ensemble algorithm is never the worst performing algorithm. Because we never know a priori which algorithm will perform better or worse in a new setting, this gives us confidence that the ensemble algorithm is a safer choice than trying to rely on intuition and picking which single algorithm to use. Finally, as the number of labeled observations increases, the ensemble algorithm is one of the best, if not the best performing algorithm across the countries. Thank you for taking the time to listen to my presentation, and I'm looking forward to the discussion.